In this session, I will explain about high-lift devices. The application of high-lift device leads to change airfoil sections and wings camber, which in turn change the pressure distribution along the wing chord. The deflection of high-lift device leads to change the airfoil characteristics as follows. Increase lift coefficient, increase the maximum lift coefficient, change zero lift angle of attack, change the stall angle, change pitching movement coefficient, increase drag coefficient, and increase lift curve slope. The figure shows variation of pressure distribution Cp along the wing chord x by c. The straight line in this graph indicates pressure distribution when the high lift device, that is flap, is not deflected. When the high lift device is deflected at an angle of delta F, the pressure distribution Cp of the wing changes along the wing chord, which is represented by the dotted line. Next is the classification of high lift devices. High lift devices are mainly classified into two types. First is leading edge high lift devices, and the second is trailing edge high lift devices. The most common leading edge high lift devices are leading edge flap, leading edge slat, and Kruger flap. There are many types of trailing edge high lift devices. The most common types are plain flap, split flap, single slotted flap, double slotted flap, triple slotted flap, and flower flap. Figure A shows the sketches of trailing edge high lift devices. The first one is plain flap. Plain flap is the simplest and cheapest high lift device. It resembles like an airfoil that is hinged at the wing trailing edge, such that it can be rotated up and down. This flap increases the lift by increasing the effective camber of the wing section. Some modern aircrafts, such as F-15E Eagle, MiG-29 aircraft, use plain flaps. The second one is split flap. In split flap, only the bottom surface of the flap is hinged so that the flap can be rotated downwards. This flap performs almost the same function as plain flap. Due to high drag generation by split flap, these are rarely used on modern aircraft. The third is single slotted flap. The single slotted flap is similar to plain flap, except it has two modifications. The first is leading edge of single slotted flap are different, and the second is it allows the flap to move rearward during the deflection. General aviation light aircraft such as Beech Bonanza F-33A and transport aircraft such as Saab 2000 use single slotted flap. The fourth one is double slotted flap. This is similar to single slotted flap, but this flap has two slots, which means the flap is divided into two segments, each with a slot as shown in figure A4. Transport aircraft such as ATR-42 and jet aircraft such as jet trainer Kawasaki T4 use double slotted flap. The fifth one is triple slotted flap. Triple slotted flap has three slots. This flap is most complex, most expensive flap design and operation. Transport aircraft such as Boeing 747 have triple slotted flap. The last one, trailing edge high lift device, is flower flap. This type of flap, when deployed, it only deflects downwards and also translates to the trailing edge of the wing. The aircraft such as Lockheed Orion P-3 uses flower flap. Figure B shows the sketches of leading edge high lift devices. The first leading edge high lift device is leading edge flap, which is similar to trailing edge flap, except it is installed at leading edge of the wing. Therefore, leading edge rotates downward, increasing the wing camber. The second is leading edge slant. This is small and cambered section which is located slightly forward to the leading edge of the wing. When deflected, basically a slant is a flap at leading edge but with unsealed gap between the flap and leading edge. Several modern jet aircrafts such as Dassault Rafale, Eurofighter 2000, Airbus A330, etc. have leading edge slant. The last one is Kruger flap. This is basically leading edge slant which is thinner and located at the bottom surface of the wing when not deflected. In designing the high-lift devices for the wing, the parameters that must be determined are high-lift device location, types of high-lift device chord CF, high-lift device span BF, and maximum deflection of high-lift device delta F max. The location and type of high-lift device must be selected through the evaluation and analysis technique by considering all advantages and disadvantages of each as per our designing requirements. The chord, span, and maximum deflection of high-lift device parameters should be determined through series of calculations. The figure shows typical location of flap high-lift device on the wing. The best location for high-lift device is inboard portion of both the left and right wing sections. The high-lift device is applied symmetrically on both sides of the wing. Deflection of high-lift device will increase the lift on both inboard sections of the wing. Both lift increments due to the high-lift device deflection will cancel out each other's rolling movement, hence the aircraft will remain laterally stable. Two reasons for the selection of high-lift device at the inboard section are: it produces lower bending movement on the wing root, which makes the wing structure lighter and causes less fatigue on the wing. The second is it allows the aileron to have large arm, which gives higher lateral control and faster roll control to the aircraft. Various designing requirements will affect the decision of selecting the type of high-lift device. The guidelines which will help the designer to make the right decision are as follows. More powerful high-lift device is more expensive. For example, double slotted flap is more expensive than split flap. More powerful high-lift device is more complex to build. For example, triple slotted flap is more complex to manufacture than single slotted flap. More powerful high-lift device is heavier. For example, double slotted flap is heavier than single slotted flap. More powerful high-lift device results in smaller wing area. More powerful high-lift device results in slow stall speed of the aircraft, which means safer flight. If the high-lift device need to be selected for heavier aircraft, then the designer must select more powerful high-lift device. More powerful high-lift device is selected, it results in shorter runway length during takeoff and landing. More powerful high-lift device allows more powerful aileron. The simple high-lift device operates at simpler mechanism compared to more complex high-lift device such as triple slotted flap. Span-wise extension of high-lift device depends on the amount of span required for the ailerons. That span required for ailerons depends on aircraft lateral controllability requirements. High-lift device span is represented as the ratio of high-lift device span, that is flap span BF, to the wing span B. 50% of the wing span is taken as the initial value for the span of high-lift device. Exact value must be determined through the calculation of lift increment due to this span BF for the high-lift device. Aerodynamic technique known as lifting line theory can be used to calculate lift increment for each span of high-lift device. The high-lift device span BF can be adjusted to achieve the required lift increment. Structural integrity must be considered while allocating part of wing chord to the high-lift device. Device chord is defined as the ratio of high-lift device chord, that is flap chord CF, to the wing chord C. The deflection of high-lift device leads to increase the wing drag. Thus, high-lift device chord must not be so high that drag increment due to its deflection cancel out or nullify its advantages. High-lift device chord in turn increases the power required to deflect the high-lift device. Suppose the pilot uses manual power to deflect the high-lift device. Longer high-lift device chord requires more power. Therefore, shorter high-lift device chord is better for many such reasons. Device chord and span can be interchanged to some extent. If the designer wants to reduce the span of high-lift device due to aileron requirements, he can increase high-lift device chord instead. The opposite can also be done, which means if the designer wants to reduce the chord of the high-lift device due to structural considerations, instead he can increase the high-lift device span. High-lift device chord can be extended up to rear spar of the wing. The designer can extend the high-lift device chord up to the rear spar of the wing, since in most of the aircrafts, the rear spar is important for wing structural integrity, so do not try to cut the rear spar in order to extend high-lift device chord. 20% of the wing chord is allocated to the high-lift device. Exact value needed is determined through the calculation of lift increment due to this chord for the high-lift device. Aerodynamic technique known as lifting line theory is used to calculate the lift increment for each high-lift device chord. The high-lift device chord CF can be adjusted to achieve the required lift increment. Shows side view of inboard wing flap deflection. Value of deflection must be determined through the calculation of lift increment due to high-lift device deflection. The deflection value is taken to be 20 degree for takeoff and 50 degree for landing. Theory is used to calculate lift increment for each high-lift device deflection. After that, high-lift device chord CF is adjusted to achieve the required lift increment. In wing zero lift angle of attack, alpha naught is determined by delta alpha naught equals minus 1.15 times Cf divided by C into delta F, where Cf by C is high lift device chord and delta F is high lift device deflection. High lift device parameters such as high lift device chord, high lift device span, and deflection of high lift device for several types of aircraft. Figure C shows typical location of aileron on the wing, and Figure D shows top view of the wing and aileron. The important parameters that must be estimated in aileron designing process are planeform area SA, aileron chord CA, aileron span BA, aileron deflection delta A max, and aileron location DAI. The figure shows side view of the wing and aileron deflection, and the table shows typical values of aileron parameters. With this, I will end up this session here. Thank you.